Welcome everyone. Here is part 2 of the week 1 of heat and thermodynamic unit. So this video is just going to kind of give you a little bit of an overview of why things change in temperature in something called heat. So when things we talk about heat a lot. It's very hot outside, or the thing's giving off a fair amount of heat. So when we talk about heat, heat is the transfer of kinetic energy. Now, when we talked about kinetic energy, average kinetic energy was temperature, right? So we're talking about changing the temperature. Transfer of kinetic energy from one object to another. So if you touch like your desk that you're maybe sitting at right now, and if it feels cold, the reason it feels cold is because you're transferring heat from your hand into the desk. Okay, if you grab an ice cube and it feels cold, if you grab a hot pan, you'd be like, okay, you're transferring heat. That's all about, we're talking about transferring heat. And when we talk about transferring kinetic energy, we're talking about changes in temperature, because kinetic energy was that change in temperature. So there's a couple different ways we can measure heat. The one that we are going to use is the capital letter J for joules. That's the most common one that we're going to use. There are a couple other ones. There's something called calories, right? And you know calories from food labels. However, if you notice, I wrote calorie with a little c. When we talk about dietary calories, there's something they're called kilocalories or big C calories. Oops, I spelled calories wrong. Calories. Okay, so when we talk about that, that is dietary calories. So when your food labels always have a capital C, so it's kilocalories or 1,000 calories. So there's two different ways we can really measure these. Is in science we use calories, little c calories, or joules. For our sake, we're just gonna be using joules in this unit. So which direction does heat flow? Well, if we have a hot object and we have a cold object, and we were to bring those, say, in contact with one another, like this is my hand and an ice cube, there's going to be a transfer of heat, right? So my hand is going to get colder and the ice cube is going to get warmer. So what's happening is the cold like flowing into my hand. Is the cold ice is it flowing that way, or is the heat from my hand going into the ice? And that's what this is meant to address. And when we talk about heat flowing, heat always flows from hot to cold, or we could say from a temperature that is high to a temperature that is low. Okay, it always is going to flow from hot to cold. Heat transfer always goes hot to cold. So when you grab that ice cube and your hand is getting cold, the reason your hand is getting cold is that heat is leaving your hand to go to that ice cube. So when we talk about the effects of heat flow, we can have a positive heat flow or a negative heat flow. So when we talk about a positive heat flow, what that means is that heat is going into that object. Okay, or we could say the temperature is increasing, right? So if we have positive heat transfer or positive heat flow, that temperature is heating up. If we have a negative heat flow, then we can say that the heat is leaving, flowing out of the object. I'm going to reword this. Heat is flowing out. Okay, which means that the temp is going down. Right? Heat is going in, which means the temp goes up. The temp goes down, the heat is flowing out of that object. Okay, so then we can discuss how much energy does it take to change the temperature of an object. Well, that really depends. It depends upon two things. It depends upon the size or the mass of the object, right? If we have like 2 drops of water, we can heat up those 2 drops of water very quickly, where compared to if we have like an entire lake, Wausau, to heat up, that's going to take a long time. So we talk about the size or the mass more in particular, and then we also talk in general about it depends upon the object itself. Okay, if we're talking about water versus aluminum, those have 2 different temperature or heat gain values, and ultimately this comes down to this combination of size and mass is referred to as specific heat. So specific heat is something that you talked about in chemistry, and you had a couple different activities that you guys did with it, but it's specific heat is the amount of heat it is required to raise the temperature of an object, so whether that's water, aluminum, iron, steel, whatever, a certain mass, a certain change in temperature. So if you look over here, the specific heat of water, there's 2 different ways we can do this, and we are going to use this one for our sake, but there's just want to show you, it's the specific heat of water is 1 calorie per, right, so divided by grams degrees Celsius. So it takes 1 calorie, that's a measure of heat, to change 1 gram of water 1 degree Celsius. Or it takes 4,186 joules of energy to change 1 kilogram of water 1 degree Celsius. So when we talk about specific heat, we use the variable of the letter C. And so when we talk about like the C of, say, aluminum, that's 899 joules per kilogram degrees Celsius. If we talk about the specific heat of iron, which is Fe, then we could say that that has a specific heat value of 448 joules per kilogram degrees Celsius. And then, like we said, the specific heat of water is that 4,186. So notice these numbers are very different numbers. Iron does not take a lot of energy, only 448 grams or joules of energy to change it 1 kilogram 1 degree Celsius. Aluminum is almost double that, right? So almost 900. Whereas this is like 4 times larger than aluminum. So what this is saying is water has a really high specific heat value. We talked about that in biology, that's one of the important properties of water, is just that high specific heat value. It retains heat very well, so like the entire lakes don't freeze up, but it also doesn't get too hot. So like Lake Wausau doesn't get 90 degrees, and you can say, well, would that be good? Would that be bad? Well, it'd be bad for the fish in it. So it has a really high specific heat value. So this is the equation that we're going to use for heat gain and heat loss. So Q is equal to MC delta T, and this is I believe the exact same equation you guys used with the exact same notation in chemistry, where Q represents heat and is measured in joules. M is mass, and it really, what units do we use really depends upon whether we're using calories per gram degree Celsius or joules per kilogram. Now I said we're going to use this one, so our mass is going to be in kilograms. C is the specific heat of the object, and our units are going to be joules per kilogram degrees Celsius. And then last, we have our change in temperature. Now, the reason we're going to use change in degrees Celsius because our specific heat value is degrees Celsius. So our change in temp is going to be in degrees Celsius. And how do we determine that? We use that equation. So simply going through and saying, well, my change in temp is equal to my final temp minus my initial temp. And then that's how we can calculate heat loss and heat gained. Now, if Q is, remember, positive, that means that we have heat flowing, heat flows in, which means my average kinetic energy increases, which means my temp goes up. Or if my Q was negative, then it's flowing out and the temp is going down, right? That's exactly what we had on the previous slide. So a couple problems for us to work through. So when we go through, we're talking about how much heat was gained or lost. We're going to use that equation. Q is equal to mc delta T. So Q is equal to mc delta T is the equation we're looking for. So 0.5 kilogram block of aluminum, that's our mass, at 80 degrees Celsius was cooled to a temperature of 40 degrees. So a couple things we got to keep in, we got to identify that we're talking about aluminum. So because we're talking about aluminum, we're going to very specifically talk about the specific heat of aluminum. But this is our mass. Kilograms is a measure of mass. This is a temperature. This is a temperature. Now what we have to do is we just got to remember, figure out which one's my final and which one's my initial. So if we say it starts at 80, this is going to be my initial, and this is going to be my final. And how much heat was gained or lost, we're saying Q is equal to question mark. So we say Q is equal to mc delta T, where Q is what we're solving for. We take the mass of our object times the specific heat of our object, and it's made of aluminum, so we got to use the specific heat of aluminum. It's the only one I have on this page. Those numbers will always be given. So we have the specific heat of aluminum is 899, and that's times our change in temperature. Now remember, change in temp is equal to my final temp minus my initial temp. So if my final temp is 40 and my initial was 80, we got to go 40 minus 80, so that's going to be negative. So then negative 40 times 899 times 0.5, my Q is going to be negative 17,980 joules worth of energy. So what does this negative means? It means that the heat flowed out. It left. It cooled down. That's exactly what that means. So this one's a little bit different. Still the same idea. So we have 15,000 joules of heat. That's my Q value. Is added to 0.45 kilograms. Is added to 0.45 kilograms of 20 degree. This should say water. Period. I got to do some edits, sorry. Then what is the final temperature of the water? Okay, so we're trying to determine the final temp. We're trying to determine that final temperature. So Q is equal to mc delta T, And remember, delta T is Ft minus Fi. So if my Q is 15,000, is equal to my M is 0.45, times my specific heat of water. So here's my specific heat of water. So my specific heat is 4,186. And then it's my change in temperature is final minus initial. So we are going to then say, well, that's my TF is my unknown minus my initial, which was 20. So now we can go through, we can go and take 15,000 is equal to 0.45 times 4,186. And then when we go through, this number, 15,000, divided by parentheses, this times this, we're going to get a value of 7.963, which is equal to TF minus 20. Okay, so once again, I took 40.45 times 4,186, and then I took that product and I took 15,000 divided by that number, and I came up with that 8.963. So now this is equal to plus 20, or I'm sorry, TF minus 20. So now I have to add 20 to both sides, and we get a final answer. My TF is equal to 27.96 degrees Celsius. Last problem. I'm going to have you try this one on your own, so hit pause and come back when you have it figured out. All right, so hopefully you went through and you figured this one out. If 2.6 kilograms of water starts at 20 degrees Celsius and ends at 80 degrees Celsius, then how much heat was gained or lost? So it's a heat gained, heat loss. It's a Q is equal to question mark. That's the problem. We're going to use that equation up there. And we're talking about water, so we're going to talk about the specific heat of water. Okay, so Q is equal to MC delta T. My Q is what we're solving for, is equal to my mass of 2.6 kilograms times 4,186 is my specific heat, times my final temp minus my initial temp. So 80 minus 20 is a positive number, which means heat is flowing in, right? We're heating things up, times 4,186 times 2.6, and our Q is equal to 653,016 joules. So hopefully that helps kind of explain some things. Hopefully you got that one figured out. There is a worksheet titled Heat and Temperature Changes that you should go through and work through the 4 problems that are on it. And then there's a quiz for you to finish by the end of the week. If you have any questions, pop into office hours.